And now we're gonna go to the discussion session. So let me share my screen. Okay. Okay. Concurrent Slack. Okay, so before starting the discussion, we wanted for all the STM sessions to highlight a bit the poster, the e-posters. So each of us, during each of the session, we're going to highlight 3 posters. So the first one will be the one by Bruce Balick. So because Bruce is there, can you tell us something about your poster, Bruce?
You betcha. Okay, here goes. Everybody can see it.
Yes, I guess.
This is a southern crab, and very briefly, I'd like to call to your attention that the blue in this in the oops,
Oops,
we lost
sorry.
it.
Wait. Let me do something. Wait. Yes, here. Sorry.
The blue emission here is oxygen 3. Let's see, the green emission is H alpha, and the red emission is nitrogen 2. What you see very clearly everywhere you look is that the O3 in a feature is displaced outward from the lower ionization lines. It happens also here in the inner hourglass. That is you just can't do it with photoionization. There's just no way to do it. So this is probably, if you use photoionization in the definition of a planetary nebula, this thing isn't one, but it's very definitely a nebula associated with the symbiotic. Here I illustrate the trends in O3 in blue and N2 in red on the surface of a disk. In this case, the lobes. In this case, uniform lobes. And that's the pattern that you see here. Blue out here, orange out in there. The only way I can think of to explain that is that the emission lines are shock created. Collisional ionization is taking place out in here with a wind whose speed is faster at high latitudes than it is at lower latitudes. Right? So that's called a tapered wind, and we saw an example of it in a talk earlier today, and I forget which talk it was, but it was Eta Carina. One of the speakers showed us the pattern of wind speeds in Eta Carina. So that's the point of this poster.
Okay, thank you very much. So the next one we wanted to highlight was the one by Jessie Bublitz. So I don't know if Jessie is there. I've seen it.
Hi, yeah.
Perfect.
Thanks, Laurence. Right, yeah, so my poster is showing off some data that we've working on releasing for NGC 7027. And I guess the main takeaway from this is first that we've been able to identify and contrast the environments of 2 molecules, CO plus and HCO plus formation in the nebula, as well as using HCO plus to better trace and understand the curious jets that are actively shaping the nebula itself, as well as to hint at the broader expansive spectral analysis that is going on between me and my collaborators of NGC 7027, with a lot more data to comb through and release soon. So thank you.
Okay, thank you, Jessie. And the last one is the one by Sofia Gerlova. Sofia.
Yes, Sofia, hello. Hello, can you hear me?
Yes, we can.
Okay. Our project is about the Planetary Nebula NGC 2818 and concerns its 3D morphokinematic modeling. We have we have found that although this nebula up to date was considered to be a bipolar planetary nebula, after the creation and reconstruction of H3 modeling with SHAPE software, we found that in fact it has 3 pair of lobes. These 3 pair of lobes are illustrated in the upper image on the right. Their velocities are about, their expansion velocities are about 100 kilometers per second, while the eastern lobes are approaching us. Now, in order to create a more advanced detailed morphokinematic modeling, we employed IFU data from some Fabry-Perot spectrometer from SOAR telescope. These are shown at the bottom image on the right. In this channel maps on the left, we'll see the synthetic channel maps we produce with SHAPE software, and on the right is the observation channel maps from some Fabry-Perot spectrometer. And we can see that the lobes that we have created with SHAPE software are also evident in the observational channel maps as well, something that verifies that this nebula is in fact an exapolar planetary nebula. And I also would like to present a new structure we detected in IFU data. It's in the image at the bottom left. This is an arc-shaped halo, which is evident only in the upper part of the nebula. We are still investigating this halo, and the results will be in a future completed work about this nebula. Thank you.
Okay, thank you very much. So just exit here. Okay, so if you want to know more about those posters, we have more details, so you can go and check on them. Okay, so we can start with the discussion session. So there was a lot of questions for Joel and NGC 6302. In the Slack, for example, we have a question by Denise about the nitrogen and sulfur enhancement. I don't know, Denise, if you want to develop on that.
I think Denise just said she had to leave.
Oh, okay.
Meeting.
All right. Okay, so if anyone else has questions for all the participants?
I guess, Laurence, I can chime in and say there was some interesting Slack discussion about the question of whether iron and sulfur are good shock tracers and why. And and I think that's something that's really important to pursue. You know, Bruce made a couple of arguments, I think, as to why we would expect iron to perhaps to be a better shock tracer. I may be putting words in his mouth than sulfur 2. They both have their places, and there are many studies that have talked about how sulfur 2 should show up as a shock tracer. But as Christophe Morissette has pointed out, we also can see sulfur 2 in photoionization models sitting outside the higher ionization species rather. So there is some ambiguity there, and the general question how to tease them out, you know, how to disentangle shocks and photoionization, I think is a really important one. That's kind of what we built the Hubble proposal around, with some ideas for how to attack the problem, but you know, no real solutions yet.
Okay, there's a question from Thomas who asks in the Slack, what are the state-of-the-art diagnostic tools to distinguish shock excitation and ionization from photoionization by a central star? Do you use diagnostic diagrams or tools like mappings?
That's the $64,000 question, I think, in a way. I think it would be interesting to pursue some line ratio analysis. I think that might help us there. I'm thinking by analogy with, there's been a longstanding controversy about how molecular hydrogen is excited, and one can attack it by looking at specific line ratios that are good for diagnosing UV excitation versus collisional excitation. I'll stop now because I'm sure there are more knowledgeable people than me who have something to say.
Yes, Carmen, please go ahead. We hear you really far away. Carmen, can you increase the volume?
Okay. Can you hear me better now?
No, it's the same. At least for me, it's the same.
Not really.
Cannot hear you, Carmen.
No, we can hear
Okay,
you.
maybe now better.
Yeah.
Is now better. Oh, okay.
Yeah, now it's better.
Okay. Okay. Great. Yeah, I have a question regarding the last poster that we saw.
By Sofia. Mhm.
Yes, by Sophia. Exactly.
Hello. Yes.
Hi, hello, Sophia. So yeah, you find three bipolar structures in one, right? I mean, it's like. So my question is regarding the kinematic age of these multi lobes. Is it the same for the three structures, or is it different?
Yes, because pretty much I haven't calculated yet, but pretty much they have the same velocity. So thinking about the same distances, it's about the same, yes. But still, I don't have the calculation to give you now, a number to give you now.
Okay, yeah, I could guess that the kinematic age was very similar. So I was wondering if you can comment on what is the shaping mechanism that can produce like coeval lobes with multiple directions. I mean, ejected in different directions. What is your opinion on that? Can you comment?
Okay, yes, these are, I'm still in the preliminary results and the preliminary explanation of our results. One possible scenario can be the multiple ejections and also the rotation of the central star, because how can I say, the orientation, the relative angles between the lobes are too close.
I will add here that in some young stellar objects, we also see two jets very close and probably at the same age, kind of one intermittent. I mean, you can eject in one direction, then the other. It can be, even in binary, you don't need triple if there is some recession of the jet and the companion disturb the precession of the disk that cause precession of jet, and the companion on eccentric orbit perturb the disk, for example, just an example. But we see it in young stellar objects as well, which is very interesting.
So this is something that will happen, like, I mean, some kind of perturbation or whatever makes the accretion disk change the inclination or something. But what surprises me a little bit is that this seems to happen like 3 times and that's it. Or I mean, or would you expect this to happen more times? Or
you know, binary system of interaction and then stop. Like Eta Carina had 20 years of interaction, then stop. And we see other stars doing it like a lot. Intermediate luminosity optical transient or red novae. They had an eruption and stop. Not all of them are merged, just perturbation or mass transfer, like in Eta Carina. So I think it can happen also in young stellar object. We see the jets taking for a long time, but in young stellar object, we have mass coming from a large distance. So the supplying of gas continues for a long time. In binary system, it is coming from a companion, it can be for a short time. So it's not surprising to see, and we have other with 2 very close jets. And I mentioned them in my last paper, which was not last one, 2 months ago, which was again on young stellar object with 2 jets. And I hope Jesse and Joel will join me on that project.
And you said, Noam, that this doesn't necessarily require a third companion.
No, yes, this one, yes. Thank you for who shared it, yes. So we see it in some planetary nebulae, we see it in young stellar object. And this goes again that there are many similarities when you apply jets. It's just there. It's not so clean. So
can I add something to that, Carmen?
Yes.
So in the object V-Hydra, the AGB star that we studied with Hubble, and we showed that there are bullets coming out every 8.5 years, high-speed bullets. So there we proposed something called the flip-flop mechanism. We can actually see that the direction of the bullets flip-flops every 8.5 years. And we propose that that mechanism can explain multipolar objects with lobes with similar sizes, because the axis can flip-flop between different directions every time the eccentric orbit companion goes around. So that's the way to produce lobes with roughly equal sizes. And so that's a possibility. I mean, that's along the lines of what Noam is saying, that you can do it with a disk which is warped and it's precessing.
So the short answer for that is that you need a very eccentric binary companion.
Yes.
This model might be other models. Okay?
Something you need to be able to warp the disk, and the disk has to then remember to come back to its. So the direction in which the high-speed material is being ejected, that it remembers it every time it comes around. So it goes in one direction, then goes the other direction, then comes back to the original direction, and it can be 3 directions or 2 directions, and that way you get multipolar 2 pairs of lobes or 3 pairs of lobes. So we discussed that when we were looking at vHydra, we proposed that as a possibility for multipolar objects.
Okay, thanks.
Okay. All right, we have a question by Stavros. Please go ahead, Stavros.
Thank you, Lawrence. No, it is not a question. It's just replied. Said I have already used the photoionization models from 3 million database from Cloudy and mappings. So some diagnostic ratio diagrams are coming up soon, including iron 2 line. And I have to say that there is a significant overlap between photoionization and shocks. Shocks are from mapping. So it is not an easy way to distinguish photoionization and shocks, even with iron line. Of course, other parameters like the structure of what we see from the images is something extra information. But just for the emission, I think it's not easy. And even with the line ratio, like iron 2 with bracket gamma. If this line ratio is higher than 1, it's almost certain that it comes from shocks. But if it is lower, it's difficult to say.
Okay, thank you, Stavros. Noam?
Yes, I will share my screen. Okay, I would like to comment to what Bruce said in his talk, that we might need to change the paradigm. This is from an old paper for 2006. You see here 2 similar nebulae. One is cluster of galaxies, the upper one. This is an X-ray image, but we know that the clean red is high emission X-ray, yellow, green, and then blue. So you see the jet in the contour. Clearly jet even tilted to the direction of the empty lobes. So we have here precession and have here jets cleaning bubbles, give you this butterfly shape that I also see in this planetary nebula from Sahai. So this is one image. Another one is something I also showed, and this goes to this, again, cluster of galaxy, and this is a planetary nebula. We see really jet that is precessing, and after a shock, it's breaking its direction. So and this is, again, this is an ILOT or red nova, illuminated nova. Again, I showed it in my opening. You see nice bipolar structure, but complicated inner structure. So I don't think we need to change the paradigm. My view that we only need to change the type of mass transfer that we have from the AGB or post-AGB star to the companion. And in symbiotic stars, binaries, we have a mass transfer from the wind or Roche lobe overflow. And I think in these systems that Joel and Bruce presented today and in the posters, we have more violent mass transfer. And I think it is right that if it gets into the common envelope, the jet will not go out. So I think what we have is a grazing envelope evolution, which I might comment more tomorrow, where the companion really grazes, goes around the envelope of the AGB star accretes at a very high rate, even more than Roche-Lobe overflow, and has very strong jets, and because of the strong interaction, you have disk precession and so on. Now, this interaction can commence, have a strong interaction, the jets remove envelope mass, and then the system get disconnected for a while. So then the injection of in short time that will give you a linear radius velocity relation can repeat itself several times, not only once. So even if we see different kind of subject of type of morphology, some of them might be ejected in a short time with period of separation between them. So we don't need to change the paradigm as saying, Bruce, we only need to be aware and open to many, many possibilities of mass transfer, eccentric orbit, in some cases triple star, but here we'll talk only in binary because we see precession and nice loads. And this is what I wanted to say.
Okay, thank you. So I think that if there's no other comments for this session, I think that we're gonna end there. Martin, I don't know if you have some announcement or any other.
Well, just remember people that tomorrow we are meeting at 10 a.m. GMT. So we are meeting a bit earlier than these days before. Remember that we have a change in the starting time of the meeting.
Okay.
And we expect all people from Mexico and California to be here.
Yeah, sure. Yes, sure.
We will think about it. We will think about it.
I'll show you later the
way.
statistics. No
way.
Okay, thank you very much to everybody for attending the meeting today. We are coming back tomorrow for more, better? Who knows? Okay, see you tomorrow, guys.
Okay, see you and thank you. Bye-bye.
Thanks all.
Bye-bye. Thank you.
Bye.